The physics of sound, air columns. You've seen these air columns before. On the left, of course, a set of organ pipes, and on the right, the Scottish bagpipes. Now, what happens is you have open and closed pipes. A close-ended pipe sets up a resonance frequency based on the length of the pipe L, but the length of the pipe is only 1/4 the wavelength of the resonant sound. So this is very important. Closed-ended pipe, 1/4. And so here's what happens. If we take a look at this particular function, this is the pipe. The blue area is the pipe. It's closed on one end. So the resonance frequency does this. This pink line or magenta line is a representation of 1/4 of the wavelength. And 1/4 of that wavelength fits in the pipe, and then it reflects and comes back. And so what we have is the length of the pipe is 1/4 of the wavelength. So you take 1/4 times L, times lambda, or if you rearrange it, you can say that the wavelength is 4 times the length of the pipe. If we take a look again, notice something has changed. I now have a different scenario where I have a different part of the wave. It's not complete, but to take a look, this piece right here is the same as this piece. And so you'll notice it comes from here to here, and then if we take the same length, it goes from here to here, and there to there. So it's not 1/4 anymore. What happens is it is now 3/4 times the wavelength. And if you rearrange this, of course, then lambda is 4/3 times the length of the pipe. If we do this again, it's going to be obvious. 1, 2, 3, 4, and yes, 5. Now, I want to make sure you understand this number right here, this 1 is the fundamental. This 3 is called the first overtone. This is the first thing that will set up resonance inside the tube that is not the fundamental. The second overtone is this 5. And I bet you could figure out what the third overtone would be. If this is 1, this is 3, this is 5, the third overtone, of course, will be 7. Now, an open-ended pipe is a little different. An open pipe sets up a resonance frequency based on the length of the pipe L, just like closed, but the length of the pipe is 1/2 the wavelength, of the resonant sound. So when we have this, you'll notice that the wave goes from top to bottom, which is half the wave. So you see this little thing that says half the wave. This is open on both ends. So L equals 1/2 times the wavelength, or the wavelength is 2L. Here's where it deviates a little from the closed-end pipe. An open-end pipe can actually set up a resonance where the wavelength and the length are the same. This is the first overtone. You have a whole wave contained within there. So we take the length and we set the number 2 divided by 2, and the wavelength and the length of the tube are equal. So this, number 1, is the fundamental. This is the first overtone, and guess what happens here? You go down up to here, and then you have a half. So it's going to be 3/2 times the wavelength gives us the length, or the wavelength is 2/3 the length of the tube. And like we did on the last one, an open pipe has a fundamental where it's 1. Its first overtone is 2. Second overtone is 3. And guess what? The third overtone will be, it would be 4. So let's do a problem associated with this. And it gets a little complicated. So just bear with me. And of course, you can pause this and back it up if you need to get more help. If a wind instrument, such as a tuba, has a fundamental frequency of 32, what are the first 3 overtones? Well, it's closed at one end. assume the same speed of sound for all the overtones. Of course, the tuba is far more complex than this, but this is going to give us an idea. So the first thing we're going to do is we're going to set up our equation. The velocity of sound is equal to the wavelength times the frequency. Now notice, the fundamental for a closed pipe, L equals n divided by 4 times lambda, or lambda equals 4 times the length divided by n. And of course, for the fundamental, n is equal to 1. Well, I can substitute now. I can substitute this value right here for lambda, and I get this as my equation. Now, this is just an intermittent equation. This is one that's in between. It's not meant for you to use in this form. But if we solve for frequency, right? We solve for frequency because that's what we're given. We notice that here is the n value. Here's the velocity of sound. 4L is in the denominator. Now, note that everything is the same except for n. So for every overtone, the only thing that changes is n. So if we take a look over here, our first fundamental is 32 hertz. That was given in the problem right here. The first, or the fundamental frequency where n equals 1 is 32. Now, the first overtone, n equals 3. So it's 3 times as big. Now notice the only thing that changes right here is this number. The velocity of sound is the same. The length of the tuba is the same. So the only thing that changes is the value n. N equals 3. So you just multiply 32 times 3. And the second overtone is n equals 5. So you just take the 32, multiply it by 5, you get 160. And the third overtone is 7. So you take 7, multiply it by 32, and you get a frequency of 224. Now, if we take a look at the same exact type of problem, but we deal with it being open at both ends. A bassoon is a little different than a tuba, but they play similar notes. So if the fundamental frequency is 90 hertz for the bassoon and it's open on both ends, we go through the same procedure. Velocity equals wavelength times frequency. The fundamental for, this should say open right here, open pipe, is L equals n over 2 times the wavelength, or wavelength equals 2L over n, where n equals 1. And now we have this substitution, this right here, substitutes right for lambda, same as we did before. And now we have frequency equals the n, which is our number of our overtone, and everything stays the same except for n. So we go over here, our fundamental, n equals 1 is 90. That was given in the problem right here. And then if n equals 2, because remember, an open pipe has values for n of 1, 2, 3, 4, 5, the integers, the counting numbers. Closed pipes are 1, 3, 5, 7. They're the odd numbers. So in this particular case, the second number two, or the n equals 2, is the first overtone, has a frequency of twice the original. The third one has a frequency of 3 times the original, and the fourth one has a frequency of 4 times the original. Now let's take a look at the first overtone of just your ear canal, which resonates with 2.4 centimeter long tube, closed at one end. The air temperature is 37 degrees, which of course is 98.6 on the Fahrenheit scale. And then it's going to ask, is the ear particularly sensitive to such a frequency? And you'll have to go back into your book and find that based on, there's a graph that I'll show you. I'll tell you what page that's on. So the first thing we do, it's a closed tube. So the fundamental for a closed pipe, L equals n divided by 4 times lambda. Lambda equals 4L over n, where n equals 1, because it's the fundamental. Now remember, closed pipe is 1/4. Open pipe is 1/2. So this is a closed pipe because it's the ear canal. So now we have to take a look at the speed of sound because the air temperature does matter. So the speed of sound is 331 times the square root of the temperature plus 273 over 273. And we get a speed of 352.7 meters per second. So the first overtone of a closed pipe is N equals 3. Now you notice it says first overtone. It doesn't say fundamental. It says the first overtone of a closed pipe, and that's N equals 3. So we get our formula. The frequency equals N times V over 4L, because it's 4L because it's a closed pipe. And that's equal to 3 times this fraction. 352.7 divided by what's in the denominator, 4 times 0.024. Remember, convert from centimeters to meters, and you get 11,021 hertz. And on page 675, you'll notice that the ear is not as sensitive at these ultra-high frequencies as it is at some of the lower frequencies. So that should help you with that answer. I hope you find this helpful.